Hello and welcome back. We continue with trigonometry. The other day I've done general solutions for trigonometric equations, mainly for year 12, but also for year 13s. Today I'm going to do a few applications. I wrote the rules here from the other day. I hope they're visible because I've done them in green. Today I do say year 12 is not actually year 12, it's more like a year 13 and possibly enrichment, because some of the equations that we're going to be looking and applying this rule are going to be fairly tough and not so obvious how to solve them. So I've got 5 equations up there, which we're going to solve them in a very strange perhaps way. So this is the first equation using these particular rules. Okay, we got the sine of 4x minus the sine of 2x is equal to 0, and we're going to be doing it in radians, so it's definitely year 13, but we can do it of course in degrees for year 12 if you haven't seen radians. So x lies between 0 and pi. Just one way we can actually solve this particular trigonometric equation for the year 13s that are aware of double angle is to actually change the sine of 4x. I'm not going to do it like that, but just give you some ideas, into 2 sine 2x cos of 2x. That's the sine of 4x using the double angle identity. And then of course minus the sine of 2x, then factorize, equal to 0 of course, factorize the sine of 2x, so you're going to get either the sine of 2x is equal to 0 when you factorize it out, or the cos of 2x is going to be equal to a half, and you can solve each bit separately and get your answer. There's nothing really too bad, so long as you spot of course this particular identity here. It's very tempting of course to just go here 2 sine x cos x, and now the question is, if you do that, what do you do with the 4x? So you don't want to do this. Okay, let's look at this equation now in a very different way using these rules. The first step for this particular equation is to actually write the sine of 4x on one side and the sine of 2x on the other side. It's minus conveniently, that's all good. Now I'm going to set up a general solution. There's my 4x on this side, there's my 2x on this side, and I'm looking at this line here. It's in degrees, but of course I hope it doesn't confuse you that we're going to be working some of the equations in radians. So 4x and 4x, looking at the argument of the function on the left hand side. Principal value, if you want, without using a calculator, is 2x, and the graph, if you want, or the rule says we must repeat every 360 for a sine, so that means 2 pi n in radians. What about the second family? That says 180 minus the arc sine of a. So for this particular one, it's going to be, we're in radians, pi, that's my 180, take away 2x, that's this value here, plus or minus 2 pi n, which of course n is 0, 1, 2, 3, and so on. I can simplify this expression on the next line. So that gives me 2x on the left, subtracting the 2x from there to the left hand side, is equal to 0 plus or minus 2 pi n. In the second equation, I want to save myself a line. I'm going to add the 2x to the left, so it's going to give me a 6x. I'm still going to have a pi there, plus or minus 2 pi n. And after that is just simplification. Divide the first equation by 2, so x is equal to 0 plus or minus pi n. And the second equation, x is equal to pi over 6 plus or minus 2 pi divided by 6, that's 3/6 divided by 6 is 60, so plus pi over 3n. And we're ready to get solutions. The interval is 0 to 2 pi. We include the 0, so the 0 is a solution. So x1 equal to 0. If we add pi, unfortunately, we don't allow pi, so this is all done. Go to the second solution, or second family rather, to pick up solutions. Pi over 6 is okay. Can we add another pi over 3? Of course we can, using the calculator if necessary. It should give us pi over 2, I hope. 30 plus 60 is 90. And then from the 90, if we add another 60, is 150, which in radians will be 5 pi over 6. And I think we'll be out. And these are the 4 solutions for this particular trigonometric equation without doing any identities, none of the sort. Okay, there is another way actually you can do this one. Some books recommend, I just thought about it when I looked at it, there are identities. Let me just write it in red somewhere. Again, not sensible really. I think the sine of A minus sine B, this identity usually are being given in the formula booklet, is going to be an odd function, so I need a sine and a cos together. 2 sine, let me just move out of the way, sine A minus B over 2 cos. One of them is going to be A plus. I just need to check very quickly by doing something in my head, which one is the plus and which one is the minus. Sine plus B, so it's going to be this identity here. So this will allow us to actually combine, that's your A if you want, and that's your B, to combine to a product. And of course, once you combine to a product, you'll be done. Okay, so that's another way, in fact, you can do that. But again, it's very, very painful. This is very, very quick and very efficient. So I hope you followed what I've done in there. And we're going to go to the second question. The second question that I've got up there involves tans. And it is the tan of 4x plus the tan of 2x is equal to 0. So for tans, there are no identities like the one I've just done a few seconds ago. So that is out of the question. So what other choices do we have? Plus the tan of 2x is equal to 0. Solution interval for this one, 0 to pi over 2. Probably there'll be a lot of solutions, that's why the interval has been shrunk. Okay, if we don't use general solutions, if we don't use this line here, what other choices do we have? There is, of course, the double angle for tan, so we can write this just very, very quickly. I'm just writing it here. 2 tan of 2x over 1 minus tan squared of 2x. That is your tan of 4x as an identity, and of course plus the tan of 2x is equal to 0. And then you're going to get a quadratic in tan 2x, and you'll be able to get your solutions from there. It's not very pleasant. It's doable. It's not that hard, but I don't really want to do that. So how can I use this method to actually solve this equation? I'm going to separate the tans into 2 sides. Unfortunately, now I have a minus. And because I have a minus, I've got a problem. Because I cannot say, like I've done with the sine, the 4x is equal to the 2x there. What about this minus? Okay. But the tan has a beautiful property. It is an odd function. So please revise your odd and even functions, which means this minus, for odd functions, I can move it inside the argument. The tan of minus a is the same as the tan of a. The same thing is true for a sine. So if you had the sine of minus a, it's the same as the sine of a. Cos, by the way, is even, so the cos of minus a, you just throw away the minus. It's exactly the same as the cos of a. So here I'm using the oddness, if you want, of the tan to write it in this particular fashion. And now I set up my general solution. So I'm looking at the 4x and the negative 2x. Only one situation. 4x on this side is equal to negative 2x with repeats of 180. But of course we're in radians again. So that's pi n, n 0, 1, 2, 3, and so on. Move the x's on all on the left, so I'm going to do it down here. 6x is equal to 0 plus or minus pi n. and that's looking very good. So my x on the very last line will be equal to nothing plus or minus 1/6 pi n, and I'm ready to pick up solutions between 0 and pi over 2. So quite clearly x is equal to 0, the number at the front works because it's equal there as well. And then we're adding multiples of 30 degrees basically. So x2 is pi over 6, x3 will be pi over 3, and there's no x4 because we're going to go to pi over 2, and the pi over 2 is not allowed. So these are the three solutions for this particular equation and in this particular interval. The next one is a cos. So I hope you're following what I'm doing. Very efficient, this method for some equations. Just need practice. And this is a follow-up from the lecture I've done on general solutions the other day. So question 3 now, it has causes. The cos of 3x plus the cos of 4x is equal to 0. Okay, solution interval, sorry, I didn't put it down, 0 to 2 pi, no, sorry, to pi, x 0 to pi. Something like this probably would be tempted, if we didn't want to use that, to perhaps use identities such as cos A plus cos B from the formula booklet is given, and it's there. It's okay, we can use that one. Actually, it's probably easier to use this particular equation. The challenge now is how we're going to use the general solution for something like this, because we have a problem. If we move one of the causes, I'm going to keep the bigger cos on the left, okay, the cos of 4x, and I'm going to subtract on the right the other cos. Now I have a problem. I cannot use this particular method because I got a minus. How about I do what I've done with the tan? Well, the answer is I can't. Why not? It's because the cos is an even function, so I cannot move this minus inside the argument. So I must find a different way of actually hiding this minus. This is a little bit tricky if you haven't seen this before. The cos, I'm going to do it in degrees, of 180 plus x is the same as minus the cos of x. You can easily verify this by your compound angle. So if you expand it, this is an identity in its own right. I mean, people that obviously at the higher level maths are preparing for sort of challenges or STEP or whatever advanced papers, the live and breathe maths basically, they're aware of this as without proving. It's to do with the symmetry of the graphs really, but you can actually prove it very easily from the compound angle. So the cos of 180 times the cos of x minus the sine of 180, and I'm doing it in degrees because it's easier to follow. Okay, sine of 180 is 0, so that's gone, and the cos of 180 is -1, so that's going to give you, of course, minus cos x. So one way of hiding this minus is to actually write this as the cos of 180, actually not 180, we're in radians, I beg your pardon, cos of pi plus 3x. So this bit is there, that's your x in this particular identity, and of course your pi is on 180. So now we can actually use the general solution in exactly the same way. So two possibilities. Principle, 4x is equal to pi plus 3x, and the graph will repeat every 360 or 2 pi n, and 0, 1, 2, 3, and so on. And the secondary for a cos, if we look at what it says in there, it says 360 minus the arc cos. So 360 minus this, or there's no 360, 2 pi, I'm going to write it in full, 2 pi minus bracket pi plus 3x, as this item here, and of course it will repeat every 2 pi n. And we want to do a little bit of a simplification now. Okay, the 3x on the left will just give us x on the first equation is equal to pi with repeats of 2 pi n. And the second one, I'm not going to put the extra lines there. Look at the 3x and minus 3x on the left, sorry, on the right. So when I move to the left, it's going to add to 7x, and it's equal to, I got pi minus pi, so that's also pi here, with repeats of 2 pi n. And this is ready, as there's nothing to simplify there. So I'll be writing it. Let me waste a line, so not waste a line, save a line rather. So what I'm going to do is I'm going to divide the whole equation by 7. So over 7, and lose the 7 from the front. So this is my general solution. And I can pick up my solutions for this interval. Looking at the first equation, I've got pi, which is I'm not allowed to have because I cannot be equal. Definitely I cannot add 2 pi, and I cannot subtract 2 pi because I'm going to go to the negative. So this particular line does not produce any solutions for this particular interval. However, the other one will produce maybe 2 or 3. So pi over 7 is okay. Adding n is equal to 1, so we're adding another 2 7s, so 1/7, 3 pi over 7 is another 1, and then it's another lot of 2 pi over 7, so it's 5 pi over 7. And if we add another 2 pi over 7 to that, we'll get 7 pi over 7, which is pi, which we cannot have. And therefore, these are the 3 answers. Let me just check with my answers up there. Yeah, that's the 3 answers for this particular equation. Nice and efficient, not messing around, very, very quick. Okay, so this was question number 3, and we're gonna go to question number 4. Question like this do come up from time to time, like the one I'm about to write now, and usually you're expected, and you're being guided usually in exams, to use your compound angle identities, your sine and cos a plus b, a minus b. So this one is, let's do this one in degrees. So we've done everything in radians, very painful. Y minus 30 is equal to the sine of y plus 45 degrees. And the solution interval, let's change it to degrees. So your y is between 0 and 360. Okay. And as I was saying, this particular equation, trigonometric equation, for year 13s, they'll say to you basically use your compound angle, they will guide you. So you expand that, and eventually you get a tan, and then you use your calculator, you get your solutions. It's a little bit tedious, but it's not that hard. It has come up. The last time I saw one of these, actually not the last time, I remember a question in 2013, which I had an involvement on this paper, but I didn't write that particular question. So let's have a look at what's the alternative in there. Sine of something is equal to sine of something. We can use this general solution here. Okay, stick this on the left, y minus 30, y minus 30. And incidentally, if you try to do this without a calculator, by using your compound angle, it will be impossible. You will have to use your calculator. This requires no calculator whatsoever. So y minus 30, y minus 30, principal value, y plus 45, with repeats of 360. Rule number 1 up there. 1, 2, 3, ... And the secondary value for a sine is 180 minus the answer that you got in there. So 180 minus bracket y plus 45 with repeats again of 360. And we need to do a tidy now. All right. First of all, if we look carefully at the first family, the first equation here, this produces nothing. Why is that? If you look carefully, the y's cancel, so you get pure rubbish. Minus 30 is equal to 45 plus or minus 360n. Total rubbish and inconsistencies. So this we throw away. What about the second one? If you look carefully, the y's don't cancel here because we've got a minus y there on the bracket once we expand it. So if we tidy this up, we're going to get 2y on the left. Make sure you follow up what I'm doing because I'm going to do a few steps at once. So that's the minus y goes to the left. And then on the right, I'm going to have 180. Take away 45 is 135. And 135 so far, add 30. I'm going to get to 165 degrees with repeats of 360. I divide by 2. 82.5. with repeats of 180. And then finally, for this interval 0 to 360, there's clearly two solutions, a y1 and a y2. 82.5, it's okay. And if we add 180, 262.5 is the second solution. So it's very, very powerful, this using general solutions, as you've seen so far. I mean, this equation, if you try to do it the other way, is quite lengthy. I wouldn't recommend actually using things like that in your exam unless it's part of your course. So if they're saying to you, use your compound angle, and sometimes there might be an in-between show, please do as the exam question suggests, because they want you to get the marks there. So don't try something to show off or something extravagant. As I said in the beginning of the lecture, yes, this is accessible mainly by year 13, not so much year 12, unless you're extremely bright, extremely clever and keen on mathematics, but it's mostly enrichment. It just gives you a different side to a different view, if you want, to trigonometric equations, perhaps one that is not often being seen. And this is the question 5 now, and last question. Sine of 2 theta is in degrees, this one. That's the only one I had planned to do in degrees. 2 theta plus 20 degrees. Plus the cos of 3 theta plus 50 degrees is equal to 0. Solutions: theta between 0 and 360. Somebody at my front door, probably a delivery. And I'll tell you what, the easiest thing to do, I do apologize for the disturbance here. The easiest thing to do, I will leave this particular question as for enrichment, and I will actually cover it. It's quite tough. Give it a go and see where you get with this, and I'll cover it on its own in another lecture. Okay, who's laughing now? I better go and open the door now, guys. See you later.